1,000-pound steel arm whips across a factory floor at 50 miles an hour, then freezes perfectly, down to the millimeter, stopping just inches from a fragile glass panel. How does it know exactly when to break? We look at industrial robotics and see deliberate, calculated movement. But that massive steel arm has zero inherent awareness of its physical surroundings. It is blind, deaf, and numb to the world around it. The intelligence driving the machine lives away from the action, typically inside a small industrial computer called a Programmable Logic Controller, or PLC. The PLC is the brain of the operation, but it is permanently locked inside a dark steel cabinet. That isolation creates a strict mechanical limit. Without a way to feel the physical environment, to know if a safety door is open or if a part is correctly positioned on a belt, the PLC cannot monitor the room or safely control a single motor. To interact with reality, the PLC relies on input devices. These external components act as the artificial eyes, ears, and nerve endings for the computer, sending a constant stream of updates about what is happening on the factory floor. This sensory network bridges the gap between the physical floor and the isolated CPU. The machines can only operate because external devices are constantly reporting the state of the room to the brain. The journey starts with field devices. These are the physical sensors stationed on the front lines of the factory, built specifically to detect the physical status and movement of the machinery. These devices communicate in two distinct languages. The first is digital input. A digital signal operates in absolute certainty. It only has two possible states. It is either completely on or completely off. Looking at this diagram of input device types, we see how physical components handle absolute states. A manual push button is exactly that, pressed by an operator or unpressed. A mechanical limit switch is physically tripped by a passing part or remains untouched. The second language is analog input. Instead of simple on and off states, analog sensors measure a continuous, shifting range of values, typically represented by fluctuating electrical currents, like 4 to 20 milliamps, or voltages from 0 to 10 volts. We see this used for tracking variables that constantly change. A temperature sensor tracks gradual heat fluctuations, and a float switch detects the exact rising liquid level inside a chemical tank, rather than just telling the computer if the tank is empty or full. Whether it is registering the heavy click of a steel lever or measuring the slow rise of boiling water, the field device has a single job: capture the raw physical state of the environment. But capturing reality presents a structural problem. Field devices operate using high physical voltages, often 24-volt direct current, while the delicate PLC processor only understands the microscopic low-voltage binary math of zeros and ones. To bridge that gap, the system relies on an input module. This hardware component acts as the translator and gatekeeper standing between the chaotic physical world and the sensitive central processor. This block diagram breaks down exactly how that translation works. A raw electrical signal leaves the field device, enters the input module, and is converted into an electrical form the PLC can actually read, a logic level of 0 or 1. As noted in this checklist, the module also serves as a physical shield. It isolates the field devices from the PLC, often using optical components to pass the signal forward as a pulse of light. This ensures a high-voltage surge on the factory floor cannot jump the gap and damage the CPU. To keep signals organized, we look at this wiring diagram. The circuit starts at the 24-volt line, passes through switches like PB1 or LS1, and lands on a dedicated address pin like IO.0. This tells the brain exactly which sensor is speaking. Without this translation layer, physical hardware and digital software remain incompatible. The input module takes physical voltages and turns them into safe, actionable digital facts. Now translated into a pure binary 0 or 1, the signal finally crosses the threshold into the central processing unit. The CPU immediately reads this new data and compares it against its custom-written program. It checks the operational rules, evaluates the state of the machine, and instantly decides what action to take next. The operation happens in fractions of a second. A physical button press sends electricity down a wire. It hits the gateway module, transforms into a digital packet, strikes the central core, and triggers a command firing a gear into motion. That sequence gives us the defining rule of automation. An input device is a field component that sends signals to the PLC, providing the information needed to monitor and control a process. The capability of a smart factory resides in this sensory network. These digital updates allow massive steel machines to function as a single, coordinated system.